Hello everybody, my name is Daniele Cattaneo, and today we'll present you my PhD work on compiler-based precision tuning. I'm now a postdoc at Polimi working on operating system, but this was my PhD work. And what is the idea? What's the problem with precision tuning? What's the deal with approximate computing? So often we need to have systems and software that performs heavy computations for performing something like simulations or prediction of things like weather prediction, or also in embedded systems. Often we need to perform computations that are very heavy for the hardware that we have at our disposal. So, for example, a fall detection appliance like a smartwatch needs to be able to integrate all the data from the various sensors in order to be able to detect whether a person is going to fall or trip down, and then in that case, for example, call emergency services automatically. And we need to do that. We need to do these tasks using as much in the most accurate way possible, but taking also into account the computational resources and the impact they have on things like battery life, or also in a data center. We might need to take into account the energy consumption of the data center to be more green and to use less electric power. So approximate computing is one way to achieve the same results, at least functionally, but using less energy and less resources. So what is heavy for the hardware depends on the application and on the hardware itself. So again, a smartwatch or a supercomputing cluster have very different definitions of what is a heavy task computationally, and have a very different definition on how to improve or make lighter any such task. So precision tuning, the whole idea is to take a generalized approach where the algorithm being used is the same, the task overall will be the same with some differences. We act at the lowest level possible, at the level of the single computation, at the level of the machine instruction. So we replace data types in a program or in let's say in the data with lower precision ones. So we are reducing the number of digits. Reducing the number of digits means generally less work, and less work means a faster computation. Of course, we also get less precision. So we have the problem of determining how much precision do we need exactly in order to be able to optimize based on that. So we have a solution space, we have a problem space, where often we only take into account the highest precision possible, but now we want to also take into account lower precisions to be able to achieve greater efficiency. So again, changing data types in a program or in the data. So the challenge is not to break the program and not to make the data useful, because if we remove all the digits, of course, return 0 and we do nothing, maximum efficiency, but we are also not doing anything useful. So the goal also is to reduce programmer interaction, because this is already done. Reducing the precision of data is already done in the industry, but it's done manually, especially for embedded systems. People need to rewrite their programs and their algorithms in order to use less precise data types. And this is very taxing, very problematic. So we want to do it completely automatically. So we take a program, then we will have a specialized compiler that will transform it in such a way as to use more efficient data representations in order to use more efficient approaches. So In the course of my PhD program, and even earlier, this has been a research effort that is being current for, I think, at this point, 5 or 6 years at Polimi. We are working on TAF, which is a compiler, a mixed precision, reduced precision compiler. So the acronym for TAFO is Tuning Assistant for Floating Point to Fixed Point Optimization. So because originally the goal was to use fixed point data types primarily, which are basically integers. So just to simplify a bit. So the goal for my PhD was to improve what we are doing with TAFO to make it actually usable in real-world scenarios and applications, and to make it, let's say, more complete in a future sense of the way. So in the original state, TAF was really a proof of concept. Now we are trying to productivize it and make it usable by the layperson. So the approaches, the things I have done are basically 3 big improvements to TAFO and the state of the art in precision tuning in general. And the first thing is a new data type allocation strategy. So data type allocation means what types go for which variable. And what type go for each variable depends on the program itself. Because again, we need to figure out what is the data type, the correct data type for each operation. So depending on the inputs and on the outputs we want, and on the error in the inputs and in the outputs, we need to sort of converge some kind of correct data type for achieving the maximum improvement in performance. So my idea was to use an integer linear programming model, which is something that is being taught about already in these sessions. Fortunately, it's a very interesting technique with some important challenges with regards to computational complexity. So what we have done is to reduce as much as possible the number of constraints and the number of factors in the objective function, such a way as to make the solution time feasible. Because of course, if we have a program with 1,000 lines and each of those lines will be transformed into a constraint or a term in the objective function, then the solution process will take 1 day, 2 days, and it won't be much useful. So the idea was to reduce as much as possible the number of instructions that then become constraints, and we employed a bit of some tricks to consider multiple data types with a single constraint, or a single term in the objective function. Also, the programmer needs to restrict as much as possible the instructions that need to be transformed. So in that way, we achieve the reasonable compilation times. And then, using this approach, we managed to finally scale our data type allocation to applications and to different platforms just by letting the user choose the platform. Then, another thing is handling mathematical library functions. So we are talking about a compiler. So inside a program, there might be calls to sine, cosine, tangent, and so on. And a compiler knows up to a certain point what you can do with those, because there are constraints on the binary interface, and there might be implementation that behave differently, and you might affect the correctness of the program. So it's a challenge to find out these functions and replace them with variants that are less precise but are still correct for the specific application. So we have done that. We have solved this specific problem by implementing a range of choice for computational algorithms. And by doing that, we achieve a 180% speed up on embedded systems by using integer-based algorithms rather than floating point-based algorithm. And the precision is adjustable. So depending on the program, at large, the correct function will be instantiated with the correct amount of precision, with the precisely needed amount of precision and not more. So finally, we have extended our approach to parallel programming and heterogeneous architectures because, again, these introduce APIs and function calls that we need to detect and handle correctly depending on their semantics. So this is not obvious, and we need to analyze the program in a very in-depth way to figure out what the control flow will be, taking into account these function calls that obscure the actual structure of the program, because once the front end will transform your CUDA program into intermediate representation, then you won't get the for loops in the point where you put them. So by using clever shenanigans with in integration with the runtime, we achieved speed ups up to 1 point, well, the slide is incorrect, it's 80% there, not 1.8%, but for OpenMP on CPUs, we get, again, speed up of up to 700% because of additional parallelization enabled by different use of processor functional units. While for GPUs, the speed up is much more limited because GPUs are very efficient for floating point types already. We use 16-bit floating points instead, and that gives us 80% speed up. So what you have learned in the end is that precision tuning has specific areas in which it excels at improving application performance and energy efficiency, especially embedded, which is unsurprising. That's where most of the efforts have already been concentrated. For HPC, it's not so easy, but our results on GPUs are encouraging for future work. What we need in the future to optimize the energy efficiency of our computing systems is dedicated hardware with built-in support for precision tuning, and also novel compiler infrastructures that allow us to perform precision tuning and program analysis in ways that are more efficient and more general. So, thank you for your attention. It was a bit technical, but I hope it was interesting anyway. So, thank you very much, and questions later, of course.